Okay, so we're looking at image formation by a converging lens. Okay, so we have a nice little simulation right here. We've got a converging lens right here. We've got the pole of the lens right at the center. We've got an optical axis right here, and here's our object in blue, and here's our image in green. And we've got a scale down below here, and the numbers on this match up with the numbers over here. Okay, just in these fields. Okay, so we've got the focal length of 10 centimeters, which we can alter. We've got an object distance of 33.2, which adjusts by just sliding the object, and you see the image changing as a result, and the numbers changing. We've got an object height of 18 centimeters if you want to do comparisons for magnification, etc., of the image to object, etc. And then finally, you've got your image distance, which is important for the and finally, you've got the image characteristics. In this case, you've got the real, inverted, and reduced is the way it's described here. Okay. Okay, now by convention, an object, the distance from the object to the optical axis right here is taken to be positive when the object is on one side of the lens and the image is on the other. So this is also taken to be a positive distance right here, the distance from the optical axis to the image. Okay, so that's taken as a positive distance as well. However, by convention, if the image appears as a virtual image on the other side of the optic axis, i.e. on this side, then what it means is the image distance is negative. And I just demonstrate that then by changing the object distance inside the focal length. So here we go. And okay, so there we go. Now I'm just approaching the focal length, and here we go. So here's the image reappearing then. Okay, and because it's on the same side of the lens as the object is, this is taken as a negative. So this is a minus distance by convention for the image distance. Okay, so that's important for the lens equation that I'm just going to mention briefly right now. Okay, so the lens equation then is 1 over u plus 1 over v is equal to 1 over f. Now u corresponds to the object distance. Okay, so the object distance is u, and the image distance, of course, is v, and then the focal length is f. Okay, so we can do a test on this, and we can test our values right here. So I'm just going to change this back to this, and we're going to test with the values that we have for our current conditions right now. We've got an object distance of 26.4 centimeters. We've got an image distance of 16.1, and we can use 1 over u plus 1 over v in this case then, and sub our values in and check to see do we get the number 1 over 10, and if we do, we know that our lens equation works. Alright, so let's punch in those numbers then. Object distance u is 26.4, so I'm just going to do a type in straight away then. Okay, so it's 26.4. I've got to invert it because it's 1 over u. Okay, so there we go, and plus the image distance is 16.1, so do a type in 16.1, and again do 1 over, and that's going to be 1 over v, give an equals for that. This is the number that we get. So this now is equal to, because 1 over u plus 1 over v is equal to 1 over f, okay? So this is equal to 1 over f. And if this is indeed 1 over f, okay, then if I invert the 1 over f, I should get the number 10.0. Okay, so I'm going to do that straight away. And perfect. We get 10.000. So to 3 decimal places we've got zeros, and it matches this perfect. The lens equation works, and we've just confirmed that then. Magnification is simple to calculate as well. That's simply just, it's the image height over the object height. And in this case, if we do 11.8 and divide it by 19.4, you're going to get a fractional number, so that would mean that it's been reduced, it's been fractionated. You've also got the power of a lens as well, and this is a pretty interesting thing as well, and it's related to the focal length. Okay, so what it means is that how short is the focal length? Because the shorter your focal length and the more powerful the lens. This is one of these inverse relationships again, meaning that P is equal to 1 over F, and F is under the line, so the larger F, the smaller will be P, and that's an inverse relationship. So basically, if you've got a lens that can focus the rays to a very short focal length, it's a powerful lens. That's the idea. And you've got a couple of examples then for that. And just finally to say that it's really important that in ray tracing, to find the nature of images, it's just important that you know 3 rays, or work with 3 rays. The ray that's parallel to the axis, a ray that goes through the optic center, goes straight through. The parallel ray goes through the focus, the focal length, the principal focus, and a ray that's going through the principal focus on the object side of the lens emerges parallel from the lens, and where the intersection of those 3 take place, you get your image. And notice that it's inverted, and the same thing happens with any lens, convex lens that is, that you get an inverted image in actual fact of the object, and then that has to be righted in your optical instrument, whether it be camera, telescope. Well, in fact, in telescopes, in a lot of cases, their image is not inverted because it really isn't that important. If you're looking at celestial bodies, it matters not too much whether it's inverted or not, as it would for the image of a person you were looking at. That would be important that they would be upright.